Finally, as promised, we're going to discuss the rule for the derivative of f of x equals e to the x. What is the derivative of f of x equals e to the x is the question. Let's check it out again. If you've had calc, you probably know this already. But in savor the rediscovery of why it's true. If you do already know the answer, for the rest of you, who knows what it could be? Let's see. We're going to start again, of course, with the definition of the derivative. So we have f prime of x equals the limit as h approaches 0, e raised to the x plus h minus e to the x all over h. Interesting. Definitely never had to solve one of these where x plus h was in the power of e. What could we possibly do with this in order to clean things up? And so it's pretty clever. If you think of that e raised to the x plus h, rewrite it this way. E to the x plus h is the same as e to the x times e to the h. And so we have limit as h approaches 0, e to the x times e to the h minus e to the x all over h. Why would this be true? Well, right, if we were to multiply here, if we were to simplify this, wouldn't we add the exponents and pull it into 1? So why not move back the other direction and split it up? We can do that. What's the usefulness in there? Notice now, e to the x can be factored out of that numerator. All right, e to the x, e to the h minus 1 over h. So factor out the e to the x, and then notice we can actually move that factored e to the x all the way in front of the limit. Let me explain that. Why am I allowed to move e to the x? Normally this is you have to be very, very careful if you're going to do this. I recommend don't do it. You're better off just not ever doing this because people tend to abuse it very quickly because they're not sure what to do. They're like, oh, I'll just pull it all out. And then like, oh, no. Okay, so 99 times out of 100, don't do this. Here's why we can get away with it here. Because e to the x does not have any h's. The limit is h approaches 0. So if I've got something factored that doesn't have an h, then the limit doesn't affect it. Right? The limit of as h approaches 0 does not have any impact on e to the x. So if it's factored, I can continue to factor it out in front of that limit. So the only thing the limit influences is here, including the minus 1 because I've got subtraction. Like this was being multiplied. That's a different story. Okay. So hopefully you're with me there. Now the question becomes, can we perform this part of the limit? And if we can figure out what this comes out to be, well, then we're just going to multiply it by that guy and we have our answer. So it's a lot easier if I could go to Desmos right now and would just do this graphically. So it turns out doing this algebraically is rather difficult. So for the purposes of our lecture, when we're in a normal class setting, I've got Desmos pulled up, in the room, and we just graph what we see right here, e to the h minus 1 over h, and we see what happens as h approaches 0, and that's pretty convincing. So I'm going to put that in the Desmos video as well. I'm just going to kind of spoil it. I'll just tell you what would happen if we were to graph that and look at h approaches 0. Obviously, it's a whole, but where does that y value approach? And it turns out it's 1. So this whole thing, that limit is going to be equal to 1. You could convince yourself with a table as well. Well, hey, e to the x times 1, that's just e to the x. So we have it. Now, this should just blow your socks off. Why? What was the original function? F of x equals e to the x. What's the derivative? F prime equals e to the x. Here's the rule for e to the x. the derivative of e to the x equals e to the x itself. It doesn't change. Oh my goodness, that is crazy. What is this? So it turns out that e, that number e that we're introduced to way back in algebra, was like 2.71 something something something. A number kind of like pi, got these decimals going. So that number, nobody considered, nobody thought was, they didn't even recognize it. Like you just didn't think about that number until calculus came along and people started investigating, is there a function out there whose derivative is itself? And eventually people realized it's e to the x, and e became this super, super important number at that time. And then people realized all these applications for it, and it became this massive thing. But not until calculus, not until people asked that question: is there something out there where this would be true? And they weren't just asking that question out of curiosity; they had good reason. It is kind of interesting, but they had a motivation behind it for modeling population growth and that sort of thing that we see E used in back in algebra. Okay, we're going to finish. That's our last rule for 3.1. We're going to finish with one quick example, taking a derivative. Let's say g of x equals 16 x to the 8th minus 5 e to the x. What's the derivative? Implementing our new formula. Here it is. Well, this part, the power of x, we're going to multiply the 8 down. 16 times 8 is 128, and it's x to the 7th. And then 5 e to the x, we've got the minus comes down. The 5, constant multiple, it just carries along. And the derivative of e to the x is e to the x. So there it is right there. G prime of x equals 128 x to the 7th minus 5 e to the x. That's it for 3.1.